Okay, we're going to jump right into the orbital unit and carry on with the sophomore physics Earth, which has a certain appeal to it because, first of all, mathematically the potentials outside and inside are solvable because of a deep symmetry that they have, deep and quite different. One being the unitary 3, that's the inside oscillator world of 3 dimensions. And then the outside world is 3-dimensional Coulomb interaction. That has a 4-dimensional orthogonal group symmetry that makes it solvable. The thing we're going to do today is look at that one. We've certainly spent a lot of time on the oscillators, and we're going to come back to oscillators and waves toward the end of the course, where we really make a connection of classical mechanics with quantum theory and relativity at the same time. The thing that I want to do today, and it's sort of spelled out right here, is to do both the isotropic harmonic oscillator and the Coulomb orbital algebra side by side. So you see that in the third screen there, in the fourth screen. We're going to look at the spatial and time solutions, their connections to conic sections, that is, ellipses and hyperbolas. But it's the Coulomb one that comes up with hyperbolic solutions that are well, complicated if you look at it wrong, very simple if you look at them right. Today we're going to look at them wrong. We're going to do the algebraic, the normal algebraic approach for both of these. Then the next lecture, that's on Monday next week, I'll show you where the symmetry of the Coulomb field makes what we do today trivial. But it's a good thing to see the non-trivial solution, since that's the one that connects with some of the things that you do in astrophysics, and also if you're an atomic physicist, you need to know some of the things that show up there as well. And while we're doing this, there is what I call a mystery similarity between these two problems. It's called the Kustenheimer-Stiefel connection, and it's very obscure. But I'd like to show it to you in an elementary way. Okay, so hopefully we'll get to the point where we actually get the geometry of this going, so that we can do what comes in the next lectures. Now, we have now 2 first pages. That's page 2 and 3 in the lecture notes. We'll have links. We just have run out of space, so got to get another page going. Okay, so the first thing I want to do is just look at the effective potentials again, and maybe quickly run a simulation that we've seen before, but it's going to, certainly the one for the Coulomb is the one that has the most complicated structure, the way we're going to do things today. So taking any isotropic potential, any potential that's just a function of radius rho. I'm imagining cylindrical coordinates here. I really don't need to take into account the polar coordinates. Don't need that complexity. All I need is rho rho and phi phi, and I'm good to go. Because all of the classical mechanics that we talk about will be orbits, and this would be true for any isotropic potential, will be orbits in a plane. So you throw the thing with a given position and a given vector, that forms a plane, and it stays in that plane forever. There's nothing in isotropic to pull it out of the plane. So that's a symmetry in itself that's very important, and with that symmetry, we then have a conservation of the angular momentum, the phi momentum, p phi here, m rho squared phi dot. That's a constant. We're just going to use the letter mu for that. Greek for M. It would be the magnetic quantum number if this was a quantum mechanical problem. M is often used as the magnetic label for angular momentum in the z direction. So that is the situation for any isotropic. We've got a thing here, but we're interested in two very special isotropic cases, the Coulomb and the oscillator. The inside of the sophomore Earth, and then the outside, the rest of the universe, involves this particular thing. Now, it's a modeled universe in which there's only one big mass that we're going to be doing orbiting around. But I should note that if we're talking about an elementary model for a neutron star, one that's not doing weird things, and one that you wouldn't hear from because it would be quiet, but most of them aren't very quiet. But in any case, the idea would be that the nuclear matter would start at a certain radius and be very sharp, it would be very, very spherical. So the mechanics of that would be pretty close to this sophomoric model, and we're interested in things that are orbiting around that in this case. So the outside of the neutron star would, to some degree of approximation, be described by this energy function right here, that has the effective potential that involves not just the Coulomb potential, but also the centrifugal barrier. And then this one is the same way. We're going to use the same coordinates to solve this, resolve this problem that we've done already a number of ways as we use for this here. Now, a couple of things to mention here. What this plot is showing, this particular thing, are negative values of the potential. This is an attractive potential. So, in each of these cases that we're doing, the oscillator on the left-hand side and the Coulomb thing on the right-hand side, the K for the oscillator could be negative, but then it wouldn't be an oscillator at all. It would be hyperbolic cosine solutions repelling away from something. We're going to study that later using hypocycloids and things like that briefly. But for now, that K is positive. Here, K could be positive or negative, but what we're showing it here for are negative values of minus K. That is, we're going to assume an attractive potential, and for this particular go-around, an attractive potential has positive K, and you have to put the negative sign in there to do the attractive case. So I call this make this point very clear, because we're going to be consistent about this. Attractive if K is positive, but what we really mean is minus K is negative, and this thing is a negative quantity. So we need the explicit minus sign. I'm just making sure that this is very clear. We have an explicit minus convention here for the Coulomb. And we have to worry about it for this one, but we do have to worry about it for that one. Okay, that said, we're off to the races here. Now, just quickly, and I'll do it on this machine right here. I'm going to back up here where I have a link at the bottom that you can click on yourself when you get these lectures off the net. But recall what it looks like when you had an oscillator with the effective potential added into the oscillator parabola, and you make your ellipse in a fairly complicated factor, that is, you describe what's happening if you could ride on that blue line and watch the thing go to its apogee, its upogee, and then to its downogee, the perigee, and then back again to the apogee, there it is, and then back again to the perigee. So just to remind you that that's what's going on in that case. Here, I'm going to see if I can get the Coulomb one to go here real quick. I just clicked something.
Advance the page.
There we go. Let me get that going and see if it'll work on here, and I'll play these against each other. In any case, the things that we're going to be discussing that are new involve this one, but we did look at this briefly before when we were doing the introductory unit. Okay, so we have an effective potential now that this green line right here that has a dip in it, and if you want circular orbits here, you have to set this thing down as close as you can to the very bottom of that potential. I'm trying to do that, a little nervous here, to try and get that arrow right on the bottom of that thing. Click. Okay. I haven't ever done it that well. That's within a pixel. So there's your circular orbit. But all of the orbits, however bizarre they are, and I can come and start this thing way out here, and actually gave it a little kick in that direction, had some momentum in that direction. But now we're talking about something way off the screen here, but here it comes, okay? And that's an ellipse that goes bang around there, and when it goes bang around there, it bangs around a circle here, and we have to derive this. This is something that we won't do today. That's where you really need the symmetry analysis of the Coulomb field to understand. Okay. Anyway, this is what we're dealing with. So most of this is going to be a dreadful algebraic lecture. That's just the way it goes sometimes. I want you to see the old-fashioned ways as well as the new ways for all of the things that we do. So let's bring us back here to the lecture and bring us back here to where we're going. Okay, so let's get the algebra going here. I'm going to do it on all three screens, try to keep these things. And just to remind you what it is we were doing in Unit 1, there are the three steps from inside the sophomore physics Earth to infinity, and they're equal. And this is a picture that occurs in Unit 5, but we did a lot more details about that structure before. Okay, so let's get started here. One of the first things that you do in effective potential, or any potential for that matter, is look for a stability point. That is a point like I was trying to point out here, where the thing would just sit there in the effective potential plot. And that's what I'm talking about right now. First of all, for the oscillator, the homogeneous isotropic harmonic, beautiful, perfect oscillator. Now, depending on how you set your initial conditions, you're going to be either on a high energy part or lower energy part. Anyway, you want to find the bottom of that. And you ought to do the same thing with the Coulomb. Okay? So, looking for stability points, and then we're going to do them together here for both of these potentials, the points where the derivative of the effective potential, the actual driver, is zero. Okay? And so we have to solve this equation for the derivative of this being equal to nothing. And solve for it, solve for the radius that where that occurs. Okay, so
basically what you're coming out here with if you go ahead and take the square root of this thing and get a rho stability. At the square root of the angular momentum divided by the mass times the spring constant here, the Hooke's constant. And then the Coulomb constant K shows up here in the numerator of the Coulomb force. We're talking about derivative of potential, so we're using force units right here. And that one it comes out with a mu squared equal to plus K rho times mass. And I put the mass in the denominator of the thing. So that's what we're dealing with here. And the idea, of course, is that at that point, and around that point, you have some oscillation if you're not quite at the bottom. And that is what we're calculating next here. And that's the actual second derivative divided by the particle mass, square rooted. Okay, so we get two results here that are, well, comparable in some sense. This one right here, 2 times K over M. Well, we know this is an oscillator, but you get an extra factor of 2 because this thing, well, it's just the geometry of the fact that the picture, this plane here rotates if there's any angular momentum at all. So that makes it interesting, to say the least. A factor of 2 shows up here. Whereas this one is a little bit more complicated. It looks more complicated, but what we're noticing here is a frequency that's kind of weird. It's got the angular momentum mu cubed. It's got the K squared instead of here being a square root of K over M. So at this point, the two problems look really very dissimilar. But they're really only dissimilar by being factors of 2 different. So we actually work out the frequencies that go with these two oscillations at the bottom of an effective potential. This one comes right out to be good old Hooke's angular frequency, the square root of that constant K over the mass. Whereas this crazy thing here, this dot thing here, this one comes out to be a phi dot, that's frequency, the angular momentum divided by it's basically an inertia. But you clear all those factors out, and you've got a K squared over the angular momentum cubed. Then quite messy. But the thing that you notice is that these two are equal, whereas these two are factor 2. Okay, and that has to do with the fact that this one has 2 apogees and 2 perigees. That guy only has 1. Okay, so that's a very big qualitative difference, but you can see it is also that analogy. Now, later on, we're going to get the time equation for this whole thing, and that's 3/2 Hauer law that actually gives the frequency that an astronomer would be looking for. But right now, we're just getting the results that fit this particular effective potential algebra. Now, if you want the frequency, at least you want to see a little bit more about what the frequency is. I'll go ahead on this one. I pointed out 2 to 1 and 1 to 1 there. But here, if you think of this thing as a force law, K times R, then the frequency is the K square root of the K of the gravitational potential that is inside the Earth. That's an R over R cubed, basically. But this is the density part, and then this is the R that you're actually talking about. Then outside of the thing, the Coulomb, it's this thing. You begin to see where you're going to get a 3/2 power of something anyway as your frequency. So that it said, let's go on and get this thing off to what we need next are the turning points. We were just looking at the bottom and its curvature, but now what we need are apogee minus perigee. This distance right here, or more particularly this point and this point, those two, the up point apogee, the down point perigee, and then the same thing, we've got to look for that in the Coulomb orbits too. Okay, so that involves just a little bit more algebra than the other things. We're basically looking for the point where the kinetic energy goes to zero. And here's the kinetic energy. I faded it out, imagining it's zero. So we got to solve this equation. And basically we're getting an energy value for this particular orbit. This has some energy. And we're about to find that. And find it at the end points, the points where, if you're doing quantum mechanics, you would imagine a wave function making a transition from oscillatory to evanescent or exponential. Well, here we're just imagining this where the darn particle stops and doesn't make it into, it doesn't tunnel beyond the range that's allowed classically. So we're looking at what in quantum mechanics you call classical turning points. Okay? All right, so I've got to solve that. All right. Well, it turns out the quadratic equation, even for just a simple oscillator. So you can see why this method that we're using for the Coulomb is not readily applied in most textbooks to the oscillator. But bear with me, it's worth seeing what they both have to say. So there's the quadratic equation for the isotropic harmonic oscillator, and there is another quadratic equation for the Coulomb oscillator, or the orbiter. Okay, they're both orbiters, and they're both oscillating, but this one is doing it a little bit differently than this one. But anyway, at this point, the equations are more or less equivalent. We're seeing here things with rho and rho squared, whereas and here rho squared and rho fourth, higher powers. That is what we would like to solve, as well as there's the oscillator solutions at work. That's the solution to the quadratic equation that we get by setting the kinetic energy to zero. And then, and this is where we see this miraculous sort of connection between these two things that we have side by side here. And this is this Kosteheimer thing. Okay, basically what you're seeing is, first of all, this one is involving the radius squared, whereas this one is just involving the radius. Okay, so that extra power of 2 comes in, associated with the fact that this guy only has 1 perigee, 1 apogee. This one has 2. It's roughly what the topology of this thing is demanding. But we're also noticing that, and we'll see this in other equations that we get as we go along here, that there's this remarkable thing where the energy constant and the force constant trade positions. This is weird. Okay, this is, it's things like this you make you stay up late at night. Just make people like me not sleep well. What's going on? And so you see E goes to K here, and where we see an E, you will see a K over there. Okay, here's E squared, there's K squared for the Coulomb guy. And if the oscillator has a K anywhere, that's going to be turned into a minus 2E. Okay, so minus K turns into 2E. Okay, that's kind of weird, but okay. Let's let's see if this happens other places. And by the way, I've gone to some effort in this particular lecture, and whenever you see underline, that means that we'll go to that page, and then this is page 36, I think, right here. You can come back from that page very quickly. So this is a very lengthy lecture, and so it's worth having these little links that you can go back and forth. And I actually should put in more of them, but they do help you. Good. Okay, so that is the basic thing. This is the beginning of this mystery similarity, which appears a couple of different other places. Okay, let's go back now, and what we'd like to do is get equations for an orbit. And that's the order of the moment now. We'd like to actually have an equation of rho versus phi. And as I say, these things have symmetry, so this is possible. If I picked any other potential, say an R cubed potential, very unlikely that I would be able to write analytic functions for that. So it's off to the computer for that. Anyway, I'm going to change radial derivatives of the angle with respect to time times an inverse of a derivative of the radius with time, just into an equation that involves only the angle and the radius dot, total time derivative. And we can see very easily just by looking at, well, first of all, this equation right here is going to be driving a lot of stuff here. That's the thing that's making it possible to have an effective potential and reduce this to a one-dimensional rho problem in either case. But there's a key relation that just is standing here, the constancy of the angular momentum. And let's get both of these going here at the same time. We will then have a differential equation very easily. Total time derivative of rho, total time derivative of rho. Very similar equations except for this term. Right here, there's Coulomb, there's oscillator. Okay, and I mentioned at this time, if you click on this thing right away, you can go and get the time solution to the Kepler, well, the Kepler solution is what it is, but he did it geometrically, and we'll explain how that correlates with both the oscillator and the Coulomb thing. And it's about 10 pages long, okay, 9 pages. So there's the actual solution, but it begins here. There's a link that you can jump back and forth at this particular point here. And I think this is page 36. So let's carry on. What I want to do is use this equation to convert this time equation to an orbit equation. So I have an equation that just involves phi, differential phi here, and then the derivative of, or differential of rho and the radius and its velocity. Same thing here. Okay, so these two are pretty much the same except for this one being an oscillator, this one being a Coulomb. Okay. So there's your differential for angle, which we're going to try to turn into something useful. Okay, and this is a trick that works all the time. I mentioned in complex variables it was useful to do 1 over z, right? And that was stereographic projection where you could turn atomic and molecular physicists into an astrophysicist. People that worried about things that are out there in nearly infinity, right? And they should learn to talk to those other people like me that sitting there and looking at things that are really tiny. Well, doing this, that is, doing the inverse of rho, which we'll call u, that can sometimes make the integral a little nicer, and that does happen in one of these cases here. So that is something that we need to put down. So here are the differentials, one of them written in terms of, well, both of them written in terms of u, inverse of the radius, this cylindrical rho radius. So there's d phi. There's d phi for Coulomb. Okay. So same deal. Now I'm using little lines here to trace where the things, where the connections were made. Okay, so there's Coulomb thing. There's the effective centrifugal barrier, and
this guy came down pretty, this is pretty obvious, what we've got right here. But I'd also like to work with a thing called x. I'd like to work with this u squared, not just u, but also u squared. See if you get an equation that looks better. So we're just sort of thrashing around here, trying different independent variables, different radial variables, but squares and inverse squares and stuff like that. And you can see you get some different equations that are beginning to look like something you want to take, to integrate. So that's let's just put them all up here, because this is the messy side of this thing. And once you've done this, you see that mysterious connection again. Now you're able to go between the cases where you're working with rho squared, and you get the E changing to the K. See this E right here is a K over here, but this K over here is a minus 2E over there. So that little switcheroo of the force constant and the energy constant. Well, the force constant is also an energy constant, but something's up here. Okay, there's something going on that is kind of neat. All right, so that's where we are, and this is something that we've got to integrate, but it's an elementary integral, so we're going to do that very shortly here. Okay, quadrature integration techniques. Okay, so this is the form that we have. This one in X, this one in U. Okay, and it's got the switcheroo of the K and the E. Okay, so, one of the advantages of doing this is that you check your arithmetic. This little symmetry is still there after we've done these transformations. But each of them has this form. It's a minus, and then whatever variable you're using, x, we call it z. Here the variable is u. That would be the z if I'm going to play Coulomb. Okay, so I just have this one integral to do for both. Okay, that's nice to have that. Let's just see how it comes out. Now, obviously, that's a quadratic equation. It has two roots, so we'll write it that way. This is using the generic variable z, but we're going to be doing this with both the u independent variable and the x independent variable. Okay. So that's what we're after here now. We're actually after the trajectory for this thing, not the time solution that comes later, but just the trajectory. And that's rarely something you can do, as I am fond of pointing out here. Now, let's bring all these stuff up to date here, because that's the thing we need to do. Now, the roots are associated with the classical turning points. That's really what this physically is about. We've got classical turning points, z equal a minus b, the smaller one, assuming those are positive, z minus, that's the low, the down a g, not the up a g. The up a g is a alpha plus beta. Okay. And so we're going to be solving these two integrals sort of together here for both of these problems. So everything so far is just based on a quadratic equation that goes with the thing that's in the denominator there. Okay, so far so good, I think. Now it gets a little messy because we have to actually work out what these things are. This particular integral, though, is not messy. It's the arc sine of z minus the alpha, z minus the perigee constant, and then the beta here that goes with the apogee is sitting in the denominator. That's kind of weird, but okay, it was here and this thing was there, so that makes sense. Let's put it up here. And down here, and go ahead and finish it off in a nice form. Okay, so both of these systems have the same, in this way of looking at it, solutions. Okay, these are the directories for both of them. That's kind of neat. Okay, but be aware that when we do this, we still have to match with these different constants here, the switcheroo of the K and the E. Okay, see if I can go ahead and put this all in the context of the geometry. So we're going to be dealing with solutions that kind of look like that. That is a rough sketch of the sine solution. Okay, it comes from this arc sine integral. All right. Okay, what can we do with that? That's the big deal here now. So get the details of this. This is where it gets a little messy. But we've got it organized enough so we can control the mess pretty well. All we have to do for these two guys is tell us what is A, what is B, what is C, and what is D. Okay? D's that guy right there, A's that guy right there, B's that guy, C's that guy. Okay, so we're going to do that for the Coulomb as well as the oscillator, and they are different in each case. Okay. So here's the thing that we just were writing there, the sine solution, and here's the proper, in terms of K and M and mu, substitutions for the isotropic oscillator. And then further along here, let's get this one up to that speed. We also have the Coulomb orbiting having its values for that. So on the first go around, you get a relationship expressing alpha and beta in either case. The alpha and the beta are now ready for use. Okay, and then it's the algebraic details that are going to be on the next page. Really, most of it's on the next page, but it goes a little bit beyond that. In any case, here's what we're dealing with. And you can see this beta's got an E here and a K there in the same place, and then a change of sign, a minus 2E sitting right there. But aside from that, they're the same animal. Oh, and it's also the alpha. Alpha does it as well. Okay, the E here becomes a minus K there. Okay. Pretty neat, pretty neat. Okay, given the mess that this could have been. So here's what we end up with when we look at the solution for x. Now remember, x is 1 over rho squared. Okay. Now this thing is u. Okay. U is just 1 over rho. So you've got this 2 to 1 in the exponents. And then you've got the usual thing where the E gets replaced by K and K by minus 2E. But there are our solutions right there. That's what we're after. I haven't been following along on this, but let's get that's the next page where we actually take them all apart, make sure that I substituted them correctly. This is the messy page right here, but those are the results that we're after. Okay, so let's tabulate those things up. The messy stuff is not that messy, but I thought it'd be better to put it on a separate page than we already got so much going on here. So these are now the equations that we're after. Now I'm going ahead and I'm writing x equal 1 over rho squared the way it should be. Okay, that is 1 over rho squared, and then I'm going to, by using the mess that's on that page there, replace these with numbers that apply to the geometry.
So here's where it's nice to have some links, because the parameter table that relates the A and B of the ellipse, and you have the usual thing where the radius of the major radius of the ellipse is A, and the minor radius, well, it's out there in the off-axis. Okay, that's the B right there. Here, this is the A, and that's the B. This is pretty simple for the oscillator. The oscillator likes to have centered ellipses. But this guy, the Coulomb, puts the ellipse off-center, and it happens that it puts it so the focus of the ellipse is on center. And that's what is showing up in these equations are telling us that after you've organized everything according to that first page there, the messy page. So let's go through what the parameters are, and then we'll go through it again, because these are things that you need to get firmly in your head as we talk about how an elliptical orbit is a function of the constants that energy and angular momentum in particular determine the shape. The lambda here, we've talked about that lattice radius, the lattice rectum, if you remember that old name, where the curve cuts the axis of its origin. Where it cuts at that height right there is the lattice radius. Well, we mentioned that with regard to this, but we don't make a big fuss about the lambda, or for that matter, the other constant that's important here, which is the eccentricity, epsilon. In any case, these parameters, if you click on that when you go right to the thing which has a table of these things, but we're going to take it slow here, and we'll build. Basically, if you take the A here, and multiply it by eccentricity, that's when you get the distance from the center of the ellipse to the focal point. That is, the center of this ellipse would be, somewhere right in there. So the A epsilon is about there, and then there's another focus point that does. If this is what you call the focus, this is what might be called the prime focus. And use F and F prime when they draw pictures of these things. Anyway, this lopsided orbit, the lopsided use of focal points, very different from this one, which really doesn't care where the focal points are. Okay, anything else that I need to say at this point? This is basically the equation we derived, and this is what you get when you substitute. Now, what I need to do is give a better accounting of what the parameters are real quickly right here, and then we'll go back and do it more slowly. So this is sort of a listing of, first of all, the apogee plus the perigee radius is twice the A. That's the major diameter. Major radius is about there. Major diameter is here. So some of them, that's just 2A, but that's minus K over E. So we've got a very, very simple expression in the Coulomb world for that. Here we're doing with squares of the radius, okay? And we get that this square here is this, and that's part of the problem that I just gave today that you need to get geometrically sorted out in your head. And it's very easy to do the problem involving the rotating surfboard and the amplitude of a oscillator orbit. Now, the difference, this difference right here, and then the difference of the square, this comes out to be a epsilon for this ellipse. Okay? This one comes out to be 2A epsilon, and that's the expression for it. So this is sort of a listing here, and this is the turning points. I should have made that a link too, but anyway, there's a lot of helpful links that you can go back and forth between. mainly this one, parameter table. But just to give you a feeling here, how the parameters that define the geometry of this guy compared to the parameters that define the Coulomb is the key ingredient of all of this. I'm going to go ahead on this one, put that here too. So that is pretty much the results of what we need for the lecture today, and now we've got to turn on the geometry. So let me say something that's very simple about conic sections that makes a lot of this much clearer. I would ask any questions. Are you following this? And I know the answer to that for most of you. Yeah, I'm following kind of, but it's fuzzy. That's why I'm going to go over it again, but this time starting with a simple definition of the geometry and work backwards. Okay? So let's do that. The key thing about conic sections, and I mean all of the conic sections, circle, ellipse, hyperbola, parabola, they all define very nicely by the eccentricity. And the eccentricity is simply the ratio of the radius to the distance to the directrix. All of the conics, they all get to use this. So this is the thing you need to remember. Now we were only working mostly with a parabola. You can see right away the parabola is the thing that has eccentricity 1. Because we had to have the distance to the parabola from the focus be equal to the distance of the directrix. And then there was a kite that was made out of that, right? When we deal with the parabola. Okay. Well, the kite gets kind of warped when epsilon is not equal to 1. So the way to get feeling for these is going to be to play with the epsilon and see how it goes. So that's the definition. Distance to focus, epsilon times distance to directrix. So every point on here, including this one right here, which is kind of interesting because that means the distance here has to be this distance divided, that distance divided by epsilon here. So this is a lattice radius, this has got to be lattice radius over epsilon. And so forth. We'll walk through this thing pretty much with that in mind. But let's go ahead and put the equations that result from that definition. Okay, the idea that this r cosine the angle, this angle, that's equal to that angle, okay? The cosine of that, which is r cosine, that thing right there, okay, plus the distance to the lattice radius, that's lambda over epsilon, right here, okay, that plus that has got to be the r over epsilon. That's this whole distance right here. That's 1 over epsilon times this distance. So that's where you get the conic section equation. And that's true for all conic sections. Okay, so right away you stick epsilon equal 1 there. You got an equation for a parabola. A polar equation for a parabola, right? Real quick. Okay, is that making sense here? So it's the geometry that gives you this. This is r equal, this is another way to write all conic sections. This is the most common, the one that you use to manipulate various physical objects with. Okay, and it's the one that we just derived. So at this point we're in a sort of in a position where we can turn this equation right here, this one over, r into this thing right here, and you know, make a connection with this formula. This is only go back when my formula was derived. Okay, let's see if there's anything else I need to put up here besides getting this one caught up. Okay, so there's probably a more useful way to write that particular formula than this. Replace that with this. And so what we're seeing here is a radius. That's the r plus and the r minus, and there's two of those radii. The r minus is this radius right here that you get when you're down, the orbit is in its lowest altitude. The perigee, or perihelion, is right here, and the perigee is this distance, rho minus. And then by just the equation that we have here, here, or there, this distance right here is the aphelion. That, and the apogee is that point, and the aphelion is that distance right there. So aphelion, perihelion are given by those. That's what we make use of most in polar coordinate definition of conic section, where it's sitting with its focus over the origin. Okay, so far so good. All right, but there's a whole bunch of other relations that we need in general. As I say, one of the most important results is coming right here. Maybe I passed it. Let's see if I'm up. And let's get this one up there too. This is, if there's one thing to remember out of this whole mess, is that the energy, and this is true for all the conic sections, is minus our Coulomb constant over twice the major radius. That is, over the major diameter. The constant over the major diameter of whatever conic it is. Okay? And it doesn't care about B, the minor. Oscillator cares about that. This does not. That's, I guess, take away number one for the parameter table, which we'll get to in a minute. But that's really neat. And that's the one you look at when you're thinking about how do you think of a Coulomb orbit in a hydrogen atom, and you know the classical values that these things have. Well, okay, that should be reflected in the oscillating part of the quantum part of the wave. And this one also is kind of neat because rho plus and rho minus add up to 2A, and that's where it comes from. Okay? So, this being equal to 2A gives me that. Very, very cool. All right, well, the rest of it is kind of downhill, but still somewhat complicated. Focal axis, you ought to know, how far the focus is from center of the ellipse. That's obtained right there. Major axis 2A, but this is 2A times epsilon, the eccentricity. Let's see if there's anything else I need to throw up here. Focal axis, okay. And the difference of rho plus and rho minus, that's a key quantity. That's the 2A epsilon. Ratio of sum and difference, also important. And quite simple. It's epsilon, the eccentricity. Okay? And these are the physical quantities that give it. And at this point, you see, we've left the isotropic oscillator completely behind. Okay? We don't have as complicated a thing for the oscillator for all of these quantities. So you don't care where the focus is much. Okay, see if there's anything else I can throw up here at this point. Lattice radius, that's an important one. This guy. Okay. It's fairly complicated. It's 2 times the epsilon. I'm sorry. It's let's see if I got it here. It's it involves the energy with a factor of 2, but it's just basically a 1 minus that epsilon squared is it. And well, as I say, this is a relation that gives the total energy. At this point, we get a relationship that gives the angular momentum.
happens to be hiding in the chalk tray here, so I'll use these two screens to show it is. That is a very key result as well. But this one involves the Coulomb constant, whereas the other one, this one involves the Coulomb constant, the mass, and the lattice radius. So in a sense it requires more inputs. K and A are all you need for the energy. Okay. Well, a couple more things here, and then this is the major table that gives them all. Now, if you're working with X and Y parameters, that is, you're back using just Cartesian coordinates, oh, okay, that would be okay. And then the minor radius, which is shown right here, the B, involves angular momentum and energy and mass. So three inputs to get the minor radius, and angular momentum is important. If L is 0, then you've got a flat ellipse. So what we call a diving orbital, an S orbital, if you've got L equals 0. And that's what you have in quantum mechanics for the S states, okay? And you say, why isn't the wave function just a line? Well, it is. It's a whole bunch of lines, all equivalent, rotating, and it has an exponential shape. Remember that? But classically what's going on in there, they're all diving. Well, they dive, they go, bam, bam. That's essentially what you would do if you could make a classical coherent state of Coulomb waves. And you can. That's something we've been fooling with. Anyway, here, see, these are physical parameters. Here are the kind of parameters that the polar coordinates demand. Here are the kind of parameters that just work with X and Y dimensions. That is, A and B. Now these guys, epsilon and lambda, those are the ones that live with polar coordinates, and we are definitely wanting to use polar coordinates for the Coulomb problem. So that's it. Now this is a more complicated one here. You can see it involves the K, the L, and the E, and the mass. So you've got 4 inputs for that one. The eccentricity is a bear in that sense of demanding information. But lambda, not so bad, just angular momentum, mass, and constant. Okay, and then here it is again, in its most compact form. All right, so that essentially would be the end of this lecture, except that we really have some more things that we need to say about all of this, and I think one of them is the timing. So remember, we have now made all of the geometry that goes with just a static picture of this thing, but how does it move around on that? What's going on there? And I can give you a partial answer for that. And at first it looks like terrible algebra. I've got to do this integral now. But all of these constants, all the things I put into that thing are fairly complicated. So it looks discouraging at first that this is not an approach to Kepler's result. And indeed he didn't really have at his disposal calculus that would give a formula like that. He did it geometrically, and that's the result that you're seeing right there. And it is analogous to the result that we used early on for our oscillators, but this one is kind of a bear to derive. And that's what I'll show you if I get a chance here. Okay, so basically what I have here is this row, which is x squared plus y squared. So I put in all of our angular quantities, and it looks like I've got a mess there, but there's a good deal of consolation. I can reduce that to a thing that is more or less quite usable. I can get a thing like that fairly easily. So that's the kind of thing that I have to deal with when I take an integral here. So let's slow down here and make this happen on all of the other screens. And this is one that's showing more of the old-fashioned thing. But in any case, that is the integral that you're actually doing. But, and this is the wonderful but that comes for this particular problem, is that it sorts out rather nicely.
let's get it down there. So that's the integral I have to do to figure out how long it takes me to get to a given angle phi. That's the quadrature integral, if you will, for a given angle, starting at the nose, say, apogee, and falling, or else blasting off from the perigee to some point, say pi over 2 or pi, an angle. So it cancels rather nicely, as it turns out. Bang, 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 and you've got a very simple result. This is Kepler's orbital equation of time. And he got this geometrically. And you're seeing its geometry right there. The geometry is very similar, although important differences, to our oscillator geometry. Remember, all we had to do here, and this has got links to it, so you can go link it and make really small ellipses and watch the thing dance. But basically it involves a toe, heel, and instep of the little shoe, and this line here goes at a constant angular velocity. This line is dragged behind, and it catches up and passes, goes real fast, right at the perigee, where the velocity is really high, and then it slows back down again. This little point here got ahead of the mean anomaly. The eccentric anomaly would be this thing, and then it finally comes back again on top. The two come on top of each other as this one catches up, and then it all happens again on the loci of that ellipse for a harmonic oscillator. For the Coulomb, we're all orbiting around this. This is the center of the Earth, or wherever the force is coming from, and I am moving this thing right here at a constant, I'm moving this thing right here at a constant rate. This is the mean anomaly, and then this is the eccentric anomaly that connects to the thing right at that point. So you get a really whopping speed of that thing as you go by the perigee. Here the perigee is right here, but this is the perigee for the ellipse. So imagine dragging that thing. And I guess we said this last year, we need to make an animation like this for this guy. So let's get that on the board, just for the, something to play with. And you can imagine as this gets more and more eccentric, as you approach the diving orbital, okay, bam, bam, right? It's really quite spectacular. Okay, the Coulomb is much more spectacular than the oscillator, just because of that. Okay, so that kind of all I really wanted to do, but I've got a lot more here. We've got about 15 minutes, 20 minutes, which I'm going to just show you a bunch of pictures that you can play with yourself to get a feeling for the dimensions of the various conics and ways to think about them that are, useful. In any case, here we have our 3/2 power of the A, and then the Coulomb constant and the mass, and that's all we've got. Now that's in that particular case, it's the mass of the object that you're orbiting around. But having all points in time, I mean, you've got to really admire somebody way back when, Mr. Kepler, just shortly after Copernicus discovered we weren't the center of the universe, that he figured this out. So that's great. Anyway, let's go ahead here and just look at some pictures that have all of the dimensions that I talked about. In this case, I'll just do it for the ellipse, but then we need to see how does an ellipse change into a hyperbola. It does it in a very nice and sort of beautiful way, and we need to see all that. Anyway, here are all of the main pieces of a conic section, this particular conic section, but all of them have a focus, and then there's something going out, and if it goes all the way out, like a parabola, that's epsilon equal to 1,
And then when epsilon is above 1, something weird happens. And that's what I need you to get in your mind to understand how these things go into each other, how they're all connected. So here's an example where I've actually picked the numbers. A, this distance is 4 units. The B is 2, so it's a 2 to 1 ellipse. Okay? Then that makes eccentricity equal to the square root of 3 over 2. The lambda is just 1. There's a unit right there. Okay, the lattice radius. And then there's some other quantities that we need. And there's the equation for the thing. There's a couple more things that show you why this is lambda over 1 minus epsilon for a particular angle of 0. And then there's the other way to look at things, R plus. That's the apogee is now here over epsilon. Well, it's really big. We're at this particular angle of 0. And so forth. So there's all of the relations we've talked about, but they're more exposed here. And here's the sum of the two, and that makes a nice equation for the A in terms of lambda and epsilon. Okay, and there's the, you just put an epsilon, another epsilon factor on that, and you get the distance associated with the focal plane. And there's 2 of those focal planes for an ellipse. Now, parabola has lost one of them. Okay, and the directrix axis, and let me keep up here, because this is a full screen. This thing is in the chalk tray, and there they are. And then there's a couple of things that are worth noting that just simplify the thing. The R in the middle there will have an A epsilon right underneath it, and an A right underneath it, depending whether you're measuring from the perigee or from the focal point. Okay, so these are all interesting things when you're solving orbital problems and you want to figure out where you are. Well, these are nice points to make. This is an important one right here, where you drop a line to here and then rotate it. You'd better come right up to the perigee. Okay. So this is all stuff that I'm put in this lecture just to make it easier. Now here's the real catcher. This one I like as a way to understand, what the connection between these are. So here you go at epsilon equals 0, no eccentricity. You get a slight eccentricity, say a 0.06, I think it is, for the Earth's orbit. Okay, it's pretty small, and when you look at the thing, it's just a circle. But you get this 0.65, okay? You know, you're more than halfway to 1, 0.85, you're a lot far from 1. And then 1, just going from here to here, this end here goes to Fort Smith and past, right? Goes to infinity, okay? So the parabola has another focus, but it ain't in our space, okay? But then what happens? What if you go to epsilon equal 1.25 and you're looking for my focus, where's my focus? It's way down there, and then all of a sudden, wham, hits you in the butt, right? It comes in from the other side, right? So this is an ellipse that's been wrapped around the universe, right? This guy here goes out, somehow connects, and then comes back and hits you in the butt right here. So, I don't know whether you appreciate that way to look at a hyperbola, but that is definitely part of the story, right? Now we have to get the geometry of that thing, and that isn't easy. It's easy, but it's not trivial. Okay, so we do have to do that because we're going to use this for Rutherford scattering. That's a single really important development that led to quantum mechanics. And we'll talk about that in the next lecture. We need the geometry of a hyperbola badly for doing something absolutely remarkable that Rutherford did. Changed the whole way we look at things. Okay, hyperbolic geometry, and this is where, as I say, we need to focus, literally. In this case, I'm picking A equal 2, B equal 1, 2-to-1 ratio, and this time epsilon is square root of 5 over 2. It has to be bigger than 1, so there it is. And then the lambda comes out to just be a half unit in this particular shot here. And of course, the hyperbola we're talking about has a lambda right there. That's half of 1. Okay, so this is just getting you started, but this is kind of a pinchy thing where all these things are all scrunched together. We really need to go for maybe a little bigger eccentricity to open this up some. And then also see that there's a bunch of Thales rectangles. See what I did here. Thales rectangles sitting on their corners on circles, and it's a little bit like they're not quite on the corners there. This should be touching this circle here like this one is. So remember that when you're studying this particular thing. It's not such a problem for when I don't make everything so close as it is there. But that's just a picture. Here's one that's a little more healthy. This is a very much higher epsilon, higher eccentricity. But I do want to point out, this is going to be our impact parameter, basically. The distance that this alpha particle beam that he used from the focal point, if the Coulomb repulsion wasn't there, but obviously what's happening here is the alpha particle's been pushed off of that and is going to roar around the focus and back out again. That's the Rutherford scattering event in a classical view. Okay, so that's what we're going to be working with. And there's another one just pointing the other way. But here's the case where it's a much gentler hyperbola. We're talking about epsilon equal to the square root of 5, not square root of 5 over 2. And things open up a lot when you consider those numbers. Okay, and so now you can see different views of that particular hyperbola and its different locations. And of course, there's a continuum of different places to put that rectangle, but those three are really important. And there's the polar angle being shown and all of that. So this is stuff we're going to work with in the next lecture, and I'd like to get you to see it right away. There's the ratio to the prime focus in epsilon. There's r to the epsilon, just to see where those points are that are interesting for setting up scattering. And that's probably, since it's getting short here, where I ought to get to right away. But anyway, the B is the impact parameter. It's got a huge impact parameter right here off of the center. And the orbit comes in, and it's pretty far away from the line that it started on, the asymptote. And here its closest approach to the nucleus right there, and then it sails back out on the other half of the hyperbolic orbit. If it had been attractive, if you used anti-alpha particles, they would have come in on the sort of the other side, and we'll describe that when we do describe that experiment. But the same geometry at work here. Here you could say this is the orbit if this were attractive. So it would come in on this side of the asymptote, get that as just equivalent to the distance that one is, but now off of this focus, say there's negative charge there, attracting the alpha particle, that's what you would see. You don't have negative nuclei, so that experiment is rarely done. These are other ways to see ratio of r to epsilon, and in a case where you have all of the geometry sort of under control here. Okay, now this is amazing. This is a distance that is worth noting. That's the circle corresponding to the constant A, and then the constant B is that guy. We need to
to show that. There's another one. These are all equivalent to each other by ratios of epsilon. So there's a whole bunch of rectangles here that are now this is the one that kind of shows it, and this is the zigzag using the parameter epsilon. There's b times epsilon, there's b over epsilon. Each time you make another one of these things, you draw a circle. Next one would be a circle right to there. That would be telling you where the b over epsilon squared was, and then b over epsilon cubed, and then b over epsilon fourth, and fifth, sixth, etc. There's a geometrical series being made here, as well as here. Okay, only here I'm doing inverse epsilon. Right. Well, that's the geometry that's all over the place in this particular thing, where we have a scattering particle coming in, being repelled by this focus. That's what we'll be talking about in the next lecture. How do you get your mind around that? How do you construct it? Just a couple steps in ruler and compass. That is what I think is so beautiful about a lot of this. So, yeah, there's the zigzag that I was pointing out. Now, all of these things have the algebraic expressions. So there's the parameters that we're going to be making use of as we go through various kinds of orbits in the next lecture. But at this point, I want to show you just with two of them, A and B. And then the deal is that if I imagine strings attached to the focus, but adjustable, that is, I should build a device where I try to make an overhead projector thing that would draw orbits that were hyperbolic as well as elliptic. Elliptic's easy, you just pin the string here and put it out here, and then you just use it as a compass and it draws an ellipse, right? Well, what I did was I had to go into a geared arrangement so it released exactly the same amount of string as you pulled on it, and then you made a hyperbola, which was perpendicular to the ellipse you would have made if you frozen it. So the deal is that as you go way, way, way out here, there's a constant difference between the length that you've let out and the length of this focus and the length you've let out of this focus, until they're way out there like this, okay? And then the thing that's of interest is the distance from here to the center line, okay? That's A. That's the major so-called major radius, A, right there. Okay. Meanwhile, the minor radius, which is this one, B, okay, B is measuring. This is 2B right here, and that's the distance perpendicular to where the strings would be at infinity. So those are ways to look. The 2B is the separation between the focus prime, okay, for infinite string, infinite radius, and the original focus, this guy right here. So the difference is basically right there. That's 2A, okay? Major axis difference between these two lines. And then 2B is the difference when you let the thing go and see where the strings, how far are they apart? That's 2 times B. Okay. Well, I'm going to stop with that. Okay, that if you just make sure you come to the lecture next time with that in mind, things will make sense. Okay, that's what the geometry that's going on, and then an absolutely fantastic experiment done by Rutherford, which opens atomic molecular physics, all kinds of things. Right? Found that the nucleus was really, really tiny. And he overestimated it by factors of about 1 million. It was even tinier than what he reported, because he didn't have enough energy to get there and actually touch the nucleus of the alphas. And that'll be a problem I give you.
how much energy you have to give an alpha in order to actually see it do a weird scattering, nuclear scattering. Okay, we'll catch you later.